Welcome to part 2, balancing equations. It's my favorite thing when I get to post 2 YouTube videos. It's not annoying at all. Anyway, so here's what we're going to do. We're going to do 5 reactions today. We're going to go through kind of the same process we went through yesterday for some of them. Some of them are already translated, meaning they're already as reactions. And we're going to fix them using coefficients. If you look at that screen, you can see the coefficients underlined. It's what you copied down in the first video. But coefficients, the way that we fix them is going to be by adding big numbers in front of the compounds or free elements that we've already written. Sound fun? Historically, I've learned from teaching balancing reactions that some of y'all are really good at this. Like we get to the end of today and you're like, this is the easiest stuff we've ever done in here. And then there's some of y'all that you'll be in the middle of my AP class next year and you'll need to balance something and it'll be like, God, I still can't do this. And I don't know why it works like that. So hopefully you are the one that can do it. You don't have to write that sentence if you don't want to. If you suck at translating from yesterday, then maybe write the sentence. It's better notes. But I just wanted us to practice a little bit of translating together to remind you. There's the sentence that we're about to work on for those of you at home. Here we go. Hydrogen reacts with oxygen to produce water. Free element, and it is diatomic. Free element, and it is diatomic. The word water, we cheated. Water is a common name. It's not actually a part of nomenclature, so we just memorized that it's H2O, so it's fine. To show you how to balance this, I'm going to introduce what I refer to as the baby way to balance it because it's the best way to learn. But I really want y'all to be able to do this just by eyeballing it because most of the time balancing is a sidestep of a bigger process. But it's all we're doing today. So here's what we'll do to make sure that all the numbers are right. Step 1, I'm going to list all of the reactants as elements. So I see 2 of them. I see H's and I see O's. I'm going to duplicate that list under the products. The whole point is to get 2 lists that I can compare together, right? So I've got the H's and O's for the reactants. So I also want H's and O's for the products. And now I count. There's 2 of those. There's 2 of those. There's 2 of those. And there's 1 of those. Are you with me? Now, here's what you can't do. This looks like it would be the easiest solution. You look and you're like, well, the oxygens are off. Don't do this. So all I need to do is make there be 2 oxygens. You can't do that. All of the subscripts that appear can only come from the translation step that we did yesterday. So if we get to the end of one of these sentences and there weren't subscripts formed from nomenclature or diatomics or something that we worked on already, then you can't mess with little numbers. Don't touch the little guys. It's the Michael Jackson rule. Ask your parents. They'll tell you why that's funny. Unless it offended you, then don't show your parents. Okay. Anyway, the only way that we can fix it is by adding a coefficient. Now, the locations for coefficients are in front of substances. So there's a free element, and a compound. The reason I draw those pink lines, it's not a part of the chemistry, is that sometimes there's a confused soul out there that thinks you can put a coefficient right there, all right? And you can't, like, because you're about to want to fix the O's, and you can't do anything in the middle of water. That should be very rational, but try to address all of your misconceptions. So these are the places that we can put coefficients. Here we go. You see how the hydrogens are already balanced? Leave them alone. But the oxygens are not. Now, these coefficients that we're going to add, that we're going to insert in there, they multiply. And when you multiply things, it always makes numbers bigger when you're multiplying by whole numbers. So, in other words, if I'm going to focus on which oxygen to fix, I'm going to focus on the smaller one, because since we're multiplying, I can only make numbers get larger. So here's the question I'm going to ask myself. You see that 1 that can't be a 1? What do I need it to be? I need it to be a 2. So I need a 1 to multiply by something to become a 2. This is really rough math. What fills in that number sentence? A 2. This is the coefficient that will fix my oxygens. Where does it go? Well, I'm focused on the product oxygens that I'm fixing. The product oxygen is located right there. I can't add subscripts. I can't split compounds. The only place to put this 2 is right here. And we have added our first coefficient. Once you add the coefficient, you should then change your list. Now remember, it's multiplying, and it's multiplying times everything it's in front of. So while you're like, well, look, it fixed the oxygens. 2 times 1 is 2 oxygens. You're right, it did. But what else did that coefficient alter? How many hydrogens are there now? 2 times 2 is 4. So it didn't actually end the problem. Hey, look, our oxygens are fixed, but our hydrogens are broken. I always focus on the smaller number. It's a 2, but I don't want it to be a 2. I want to multiply it by something to make it become a 4, like the other side. 2 times what is 4? There's the coefficient that'll fix the problem. I want this 2 to affect the reactant hydrogen. The reactant hydrogen is that hydrogen. So put the 2 there. Then alter the list. All right? Don't change the list till you've already added the coefficient. 2 times 2. And you see how my lists are beautiful now? 4 and 4 for the hydrogens, 2 and 2 for the oxygens. There's a conclusion you can draw from this. There's a thing called a mole ratio that is really important for other stuff, where you simply list the coefficients in the order they appear. So the mole ratio here for this is 2, 1, 2. This is a 2 to 1 to 2 mole ratio when balanced is the way that we would say it. You'll get used to that idea at the end of each of these. Yeah? Let's do it. Said we got 5 of these today. Hydrogen reacts with nitrogen to produce nitrogen trihydride, or ammonia. All right, that would be a reverse translation. But that's not what we're focused on. Let's make some lists. You ready? Stop me if you get confused. Step 1, list all the elements that there are for reactants. H's and N's. H's and N's. Step 2, duplicate the list. Notice how I don't say make a new list. If you were to make a new list, you would list N's than H's if you did it the way it is, and then it's just confusing for your eyes. So make sure the lists look the same in regards to the order that things are listed. Step 3, count. 2 H's, 2 N's, 1 N, careful, 3 H's. We good? Are we balanced? Everything's wrong. So let's fix it. Now, this one's a little different, all right? Every problem we're going to do today is a little different from the one behind it. I'm trying just to shine a spotlight on all the types of things that can happen. Some of these are way more annoying than others. But look at the H's. Here's a question you could ask yourself. I always focus on the smaller number, right? So I want to fix the 2. Because we have to make it bigger. But is there anything you can multiply 2 by, whole numbers, to make it equal 3? It's impossible. So when that happens, when you get in a situation where you cannot easily make the smaller number become the bigger number, then you need to find the least common, not denominator, multiple. The least common multiple, right? The smallest number that they both turn into. What's the smallest number that a 2 and a 3 can both change into? They can both change into 6s. So you probably don't need me to do this off to the side. But on this side, it would be 2 times something equals 6. And over here, it would be 3 times something equals 6 to turn them both into 6s. So this, of course, is 2 times 3. I don't like the way I did that. And over here is 3 times 2. And those are the coefficients that are going to fix our problem here. So I want this 3 to affect the reactant hydrogen, which is located right there. 3 times 2 is 6. I want a 2 to affect the product hydrogen, which is right there. The only place I can put it is there. Can't split the compound. And it fixes it, right? 2 times 3 is 6. Uh-oh, but what else does that product coefficient do? Yeah, how many nitrogens are there now? Yeah, it's actually good news, right? 2 times 1 fixes the nitrogens. Is that a hand? What? Yes. This would be 3 to 1 to 2 mole ratio. I just list the coefficients. All right, so you're noticing lack of a coefficient is a 1, which you're very used to in this class, lack of a number being a 1. What do you think so far? All right, they're giving me thumbs up, all right, which is good, and I hope you're giving me thumbs up from home. The ones that are harder can get a little annoying. The thing to keep in mind is that this is a puzzle. There's always a right answer, but sometimes these steps that I'm going through, they break. Sometimes a problem requests that you think a little bit outside the box to get to an answer. So I'm going to try to show you a couple of those now. So a lot of the problems really are just as easy as these first two, though. So that's great news for you. Let's look at ones that make us think a little bit more. All right, here we go. It says sodium, and sodium, nitrate is polyatomic. Yield, sodium oxide, and nitrogen. Free element, he's not diatomic. Compound, ionic, but it's +1, -1, so nothing happens. Compound, ionic, it's +1, -2. I'm doing this faster than you might do it, but we did this yesterday. All right, so yeah, oxygen's oxidation state will crisscross to sodium. Free element, is it diatomic? Yep, nitrogen is. Any questions there? Make your list. We've got no. Sodiums, nitrogens, and oxygens. Duplicate, another no. Let's get some help counting. Let's go over to cluster 3, seat 4. Hey, 3, 4, I feel like I picked on you yesterday. How many sodiums do you see on the reactant side? 2 is the correct answer. Do y'all see the trick there? Do you see why this one's already a little different than the others? This is a split element, which is annoying. All right, you know it's going to be annoying because sodium's showing up in multiple places, which means there's going to be a couple ways that we could attack this. All right, let's go over to cluster 5, seat 6, Aspen. How many nitrogens on the reactant side? 1 is correct. All right, and then pass the bird to me, Chloe. Let's go over to cluster 2, seat 2. Hey, 2, how many oxygens? Beautiful. Over here, I've got 2, 2, 1. Does everybody agree? All right, let's check this out. Our sodiums are already fixed. That's awesome. Our nitrogens are messed up though. All right. So we've got 1 and 2. All right. Let's multiply 1 times 2. So if we put a 2 here, all right. Let's see what that changes. That gives me 2 sodiums. All right, so now we are at 3 sodiums. Do you see the 3 sodiums? Careful, right? There's 2 there and 1 there. We've got 2 nitrogens, and we've got 6 oxygens. 6 oxygens. Yeah. It affects everything that is immediately in front of the coefficient. And there'll either be a compound in front of it, so it affects the whole compound, or there'll be a free element in front of it, and it affects just the free element. Now, this messed up the sodiums. Do you see how it's doing the 2 and 3 thing again? I didn't say this last time, but when that happens, if there's other stuff to fix, if you can see that the numbers are being annoying, fix the other stuff first. It's usually the best strategy. All right, so yes, the sodiums are messed up, but the oxygens look easier to fix to me. You see that smaller oxygen number? What do I need to multiply it by to become that number? 6. This oxygen is located right there. So let's multiply it by 6. 6 times 1 is 6. What else did that change? Let's get help. Let's go over to cluster 3, C5. Hey, 3-5. How many sodiums are there on the product side right now? Product side, sodiums. 12. 6 times 2 is 12. Everybody agree? Now, here's where you have to think outside the box. Look here. Here's what your brain is going to think based on what I've taught you. You're going to think, oh, well, 3 times 4 is 12. All right. I mean, you're not wrong, but that's not the best way to go about this. And here's where I don't have a rule to teach you. You just have to deal with this. What's the best way to fix the sodiums now? I need a grand total of 12. Any ideas on what the best approach is? Put away. Not a 9. A 10. Look. Do you see how if you mess with this 2, it's going to mess up a bunch of stuff? If you change this number, it's going to change everything again, and that's real. That's called spiraling out of control. All right? But we have this sodium over here that is all by himself. He's a free element. And look. If there's 10 there and there's 2 there, what's our grand total? And we're done. This is a 10 to 2 to 6 to 1 mole ratio. A little bit more fun. Your trick is to just not get frustrated while doing it. The right answer is there. We just had to think a bit harder for a moment. Let's do another one. I'm going to keep showing you weird ones now, so don't think that, oh man, this is just getting harder and harder and harder. I'm just showing you harder ones. Make your list. CHO. Duplicate your list. Count. 5, 12, 2. Count again. 1, 2, 3. Careful with the oxygens over there. Do you see the split oxygens? You're not asking any questions. Are you sure you see the split oxygens? See how I'm getting 3? All right, it's a literal plus. All right. Let's fix it. There's the smaller number. I want that 1 to become a 5. 1 times 5. So let's put a 5 in front of the product carbon. Five times 1 is 5. 5 times 2 is 10, plus 1 is 11. Make sure you see it. Hydrogens. There's the smaller number for hydrogens. I want the 2 to become a 12. 2 times 6. So let's put this hydrogen right there, but multiply him by 6. Six times 2 is 12. All right, and then stupid oxygens. All right, careful. 5 times 2 is 10. There's 10 right there. All right, and 6 times 1 is 6. There's 6 right there for a grand total of 16. Oxygens. 2 times what is 16? You're doing so good. It's a 1 to 8 to 5 to 6 mole ratio by listing the coefficients. Sorry? Which 6? Right there. 1 to 8 to 5 to 6.
Oh.
Think you can do one without me? I believe in you. I'm going to translate it for you. Don't copy the sentence. You don't have time. Do not copy that sentence. Just write this down. Yttrium-3 chloride looks like this. Yttrium-3 chloride reacts with or mixes with sodium hydroxide. Sodium hydroxide to produce yttrium-3 hydroxide. Yttrium-3 hydroxide and sodium chloride. All right, I did all the nomenclature, stuff as I wrote it. Your job is to balance it. Good luck. You are welcome to use those lists through the rest of your chemistry career if you want to. However, it's my belief, since you hang out with me, that you're smart enough not to make lists. And if you get stuck on one, you can make the list, but y'all, this math is so simple that it saves you a ton of time to just eyeball it. And time really matters because some of y'all were running out of time on my mole test, right? So save time. Look. See how there's 3 chlorines? Okay, well, I need there to be 3 chlorines. Boom. Now there's 3 chlorines over there. See how there's 3 sodiums? Well, I need there to be 3 sodiums. Boom. Now there's 3 sodiums. You can get there rationally. And it turns out that this 3 fixed the other problem because there's 3 O's and 3 H's now, just like there's 3 O's and 3 H's that we needed. And I can very quickly get to the 1 to 3 to 1 to 3 mole ratio. Stupid 2 videos.